week we'll hear from a faculty member of the use of this one. But today I have the pleasure of introducing you to Dr. Kharitonova, who's going to tell us something about computer vision. Let's welcome our speaker.
Thank you all for coming. As you can see from the title of my talk, I will be talking about how to semantically link instructional content. And along the way, we will throw in a couple of computer vision techniques that help me along with doing that. But before we get started, I want you to think back to the last few presentations that you watched, whether in person or online. And now please raise your hand if the presenter did not use presentation slides. I see no hands. And presentation slides have become the de facto standard that we use for all of the presentations. Whether it's a classroom lecture, online course, a conference talk, a business meeting, we all are used to these presentation slides appearing on the projector screen. And this trend became even stronger once we had massively open online courses available. My personal journey with the online courses has started with an interface like this. So you have dates, you have the links to the video that was recorded of the lecture, and the link to the slides. And so I had to figure out which lecture actually covered the topic that I was interested in. So I spent a few minutes finding the slides that contained the name or the topic that I was looking for. Then I downloaded the video, and since the slide was towards the end of the PowerPoint deck, I kind of skipped through most of the video, jumped somewhere in the end, and started clicking around to see whether or not that slide flashed on the screen. And sure enough, it did show up, so I started playing the video, and the presenter looked at the screen and said, well, we're running out of time, so I won't have time to cover it today. Let's move to the next slide. You can imagine my frustration at the wasted time and the fact that I have to do it yet again for the next slides, and the video. And so, wouldn't it be nice if I could have pulled up that slide so that that's the slide I'm interested in, clicked on it, and had the video somehow magically start playing from the time that that slide was shown? Would you use an interface like this? Raise your hand if you would like something that would allow you to do this. Okay. Now raise your hand if you didn't just raise your hand. Okay, I don't see any hands. All right. So for those of you who raised your hand, I have good news for you, because this is exactly what my research project is about. So this is the interface that goes along with my research project. You have a video playing on the left and the large preview of the slide that is being shown on the right. And on the bottom are the thumbnails for all of the slides that are used in the current PowerPoint deck that the presenter is using. You also have a little indicator that tells you whether or not the slide has been shown more than once in the video. All too often, the presenter will show the slide, say something about it, and move on. And only at the end of the presentation, when somebody raises a hand and asks a really good question, does the presenter come back to the slide and give you the information you probably would have wanted to hear in the first place. And so this saves you the time, and it says, oh, these are the times when this slide appeared in this particular presentation. And if you know what you're looking for, you can use a search bar that will limit the slides to only the ones that contain the term that you're after. So this is what the interface is providing you as the user. Now, there are many other solutions that do something very similar. So what I'll do is I'll just mention a few of them that are really big names in this industry and show you how the project that I developed is actually helpful not just for the user, but also gives a lot of flexibility to the presenter. So Panopto allows you to record the screen activity on your laptop. Camtasia is actually a powerful suite of tools that allow you to put together presentations and videos and do something fancy to create a final product. WebEx does the same things for the online meetings. So if you have a conversation with your team that is on the other side of the world, there's some interlinking of the slides and the call and the presentations. MediaSide allows you to synchronize the projector, what projector is displaying and what the speaker has, by installing a bunch of hardware, linking it together and automatically syncing it. NVIDIA is a European company that is behind a very famous popular site, videolectures.net, and they allow you to synchronize the videos and the slides, and they're usually used for conference talks and famous technical presentations. And so a lot of these solutions are really great. They do allow you to synchronize the presentation and the video of that presentation. However, for a lot of them, they rely on you either installing the software that they're providing or installing the hardware that you need in order to get the synchronization, which basically means that as a speaker, I'm tethered to either the specific laptop or a room in which I can present. So if something happens and we need to switch buildings, or if my laptop, God forbid, dies, then I'm losing the fact that I can do the synchronization because the software was on that particular machine. And the fact that all of you have cell phones or we have a camera in the back recording the video is of no use for me because that original software hardware is no longer working. So flexible location is not actually also available. So far, the video looks like a very promising candidate because they don't require you to install any hardware. They don't require any particular software installation on your computer. So they will take your video, they will take your slides, but at the end of the day, what they do is they make you, the presenter, match the slides manually. Now, as a professor, the last thing I want to do at the end of the day of giving lectures is to sit there and try to say which slide was shown at each point in the video. So these are some of the comparisons of major players in the field and what my project allows me to do. So given that we know how the final project and result looks like, let's dive under the hood and see what are the gears that are helping us with this particular engine. And before we do this, let's make clear what is our major goal. So the main goal is we want to quickly access those relevant clips of a presentation. We have these slides kind of like bookmarks into the talk. And so how do we synchronize them automatically? Which then turns into a main task. We want to align the video with the corresponding presentation slides. And this alignment means that we only need two inputs. I just need the slides that you use during the talk and the video, the recording of that. Now the slides we can convert easily into images, and the video is essentially also a sequence of images played back at a particular rate, usually 30 frames per second. So we have images on one side, images on the other side, and the task becomes how do we match these images to the other images. Now, the task is kind of tricky because I have a frame and it's hard to see, but you see that there's a slide and there's a speaker. How do I tell the computer to distinguish the slide that is actually shown in the presentation from all of the other similar looking slides that they have available in that PowerPoint slide? So if we had a little more time, we could brainstorm various ideas of what would be really good techniques. In this particular case, I'll just tell you that we will be using what in computer vision we call image features. It's usually a vector of numbers that captures some sort of statistic about the image. The one that I'm using in my project is called SIFT. SIFT stands for Scale Invariant Feature Transform. And it was developed by David Lowe in British Columbia. What SIFT does is it looks at the grayscale image and it looks for areas where there is high color contrast. And it takes those patches from the video and collects them. This is what SIFT calls key points, SIFT key points. And you can see that we can have those patches from one image and they could be of different sizes. And they could have corresponding patches in another image, also of different sizes. And you can try to see how they match. And the way you figure out this matching is by using what SIFT provides you with. SIFT says, once I extract the key points, every key point I provide you with will have XY position on the image, scale and the orientation of that key point, and 128 numbers that will describe the texture around that key point. So this would be an example of one key point. We have X and Y position in the image, scale and orientation, and 128 dimensional vector explaining what is happening around inside of this particular patch. So we have the tool, we have the key points. What we do now is we look through our video. We have the frames from the video. Let's take these frames and extract these key points. This is a visualization of what the key point would look like. We have the scale, the orientation of it, and a particular location. Now that we extracted all of the key points from the video, next step would be, let's do the same thing for the slides. We can take all of the slides that the presenter provided us with and extract the key points from them as well. So what would be the next step? We have key points from the frame, key points from the slide. We want to try to match them. What would you use for matching? Any guesses? Yes?
Nearest neighbor?
Nearest neighbor, based on what?
You have a big feature vector and you're trying to see what it's most similar to?
Yeah, we have a 128 dimensional descriptor that tells us what's happening around. Let's use a nearest neighbor to see if we can find a match from the frame anywhere from the slides that we have available. And if we do this, which is exactly what we do, we find that there are quite a few matches. So we have a video frame and the slides, and these are the matches. We call them initial putative matches that we found. And you can see that while a lot of them are correct, you can tell that there are incorrect matches, something that we call outliers. And we want to get rid of these outliers because they're not serving us. They're not the proper match. So how do we do this? Well, our notion of these matches being incorrect, in particular, for example, this one, is based on the fact that we have an idea of how these points map into each other. So we have the points on the slide, let's call them x prime, and the points on the frame that are x. They're all of the different key points. Our intuition of the projection from one into another in computer vision is captured by something called a homography. A homography says that the projector screen is a plane in 3D, and the slide is technically also a plane. So we're trying to match one plane and see how it projects into the other plane. And that homography matrix says, if you give me points on one plane and you have the correct homography, they will just jump right back where they are on the other frame. So this is our setup, and we need to do something with the coordinates. We turn them into homogeneous coordinates so that we have a linear equation. I won't dive into details, but I'd be happy to tell you more about it later. But essentially, it will look like this. We have coordinates on one side, coordinates on the other side, but this is the homography matrix that we don't have. Nobody has given it to us. All we have are those locations of the key points. And this is where we bring in another tool from computer vision. And actually, for those of you who are wondering why I have x prime, but there are no x primes here, this is how you go from this to here. Just a step for those of you who are wondering. So given that we are after the homography matrix, we want to find out what is this matrix that will project those points. And the way we can do it is by using a technique called Runsack. Runsack is random sampling consensus, and it's an iterative algorithm that allows us to estimate the parameters of a model And its hallmark is that it can do it from a data set that contains a lot of outliers. So just a quick check. What is our model? Shout out. Our data set was the key points, and this is actually our model. We say that they project based on this matrix. This is the model of how these points are related. So Runsack is what can help us find out what are the values in that model, the homography matrix. So it's a really neat algorithm that essentially does guess and check. It says, let's randomly pick out those matches that you gave me, compute that homography, which we can do using linear algebra, and then see how many of the key points actually agree. And we'll do it several times until we're happy with the result, or we have enough of those key points to say that this is a really good homography. And so in the end, the slide that produces the most of those matches must be the slide that is shown in the video frame. So after running the Runsack on this spaghetti mess of initial matches, you see how it will select only the points that are valid or project back into the corresponding point under the homography that it computed. In this particular step, we get not only the slide identification out of all of the slides which slide matches, but we can also now tell where this slide should appear in the frame. So, if we know where the slide will appear in the frame, now if somebody gives me a blurry video or a video where the slide is not very readable, maybe because of the illumination, I can use something called back projection. Let's take this clear slide that we have available from the PowerPoint and use this homography to put it back into the video so that this blurry text that I have can now turn into something that is actually readable. Which means that for those of us who are watching the video on the phone and we have a very small screen, and maybe don't have as much room to flip back to the original slide, it allows us to see the text that is shown and improve the quality of the video. So this homography is actually also reversible. So I can go back from the slide, from the frame into the slide and know where that is shown, which also allows us to do other applications, such as hover over the video and see which part of the slide is, for example, occluded by the speaker who is standing in front of the projector screen. But while we're still on the topic of placing the slide back into the video, we looked at another interesting application. Let's take the video that we had before, and we know where the slide is in the video. So what I can do is now take that slide out. Why would you do this? You kind of want this slide. Well, I have all of the slides available as images, and I have the homographies that tell me where they are in the slide. And I have the correspondences between the frames and the slides. So taking out the slide from the original video actually allows me to now compress this video a lot more. This black uniform area compresses really, really well because there's a lot less information here than in the original video that showed the slide. So now, for the user who has the cell phone or who is bandwidth conscious, what I can do is I can send this video that is black projected and then send the video slides from the presentation separately. And your browser can actually put the two together on the fly without you even noticing it. So for those of you who like math, I'll give you how we do it. So the original homography we have, but then we don't necessarily want to apply it all of the time. What we can do is essentially scale the slide and maybe translate it a little bit if there is a camera movement. So we can actually use an affine transformation. We're taking away this last row that is responsible for the skewing of the slide, and saying all we care is about the scaling and the translation. And now we can just solve the set of linear equations to find this particular transformation. So that transformation basically says we'll take the slides, project them, slide corners, project them back into the video, and actually look to see how far they are from where they're supposed to be. If they're somewhere in the vicinity of it, let's just use the approximation and move the slide around by scaling it. If the change is too drastic, then we'll apply the original homography, and the user won't even notice. So when we did the experiments, we saw that in blue, that's the size of the original video in megabytes. And when we take the slide out of the video and compress it, the resulting video size is shown in comparison in black. Quite a few savings. We get anywhere from 40 to 48% savings in the size of the video. And that trend holds even when we apply pretty aggressive compression settings as well. So this is an application where we're using the same matching techniques and the same ideas between the slides and the frame in order to allow the user to download this or to watch the video without actually using a lot of bandwidth, using all of the same technologies that we had with the slide. So as I was working on this project, I was also curious, well, how useful is it to students? Will this actually help? And whether or not they would want to use this and recommend it, say, for their instructors. So I ran 2 pilot studies. In the first one, I got students in a machine learning course, and at the end of the course, we had 35 students who signed up for the study, and 30 of them who actually took the survey. So at the end of the class, they got to use the interface in order to review things, they review concepts for their midterm. I took out a lot of slides just because I want to make room for questions, but when at the end of this, we asked them whether or not they liked using the portal interface, quite a lot of them mentioned that yes, they were actually pretty happy with it. And those who mentioned that they weren't really sure commented on how they wish they had more time to actually get to use the interface before recommending it to their professors. So then the next study that I did was a lot more involved. We got 30 students across 4 different University of Arizona courses, and we did 2 experiments. In one experiment, we got the students and we had them watch a 30-minute video and then use the slides from the video to answer questions about the material that was presented. There were 2 conditions. In one case, they were using the synchronized interface, SLIC portal. In the other case, they were using basically an equivalence of the interface I showed you at the beginning. They had the video and they had the slides unsynchronized. Go ahead, you have all the information, find the answers. In the second experiment, we cut the time that they had to answer the questions basically in half. So in the first experiment where they had a 30-minute video and they had 30 minutes to answer questions, they essentially could answer the questions as they went along, simulating the case where you would have a student maybe miss a lecture and then go back to watch it again. In the second case, when they had only 15 minutes to answer the questions, that used to simulate maybe a situation when the student has seen the lecture and they're trying to get specific answers. So we wanted to encourage them to engage with the interface and use the search and use the jumping around feature. And so at the end of that, when we looked at their results and we asked them how they felt about using it, quite a few of them were really happy with it. So this is the group that had 30 minutes to watch the video and to answer the questions. The one that was really rushed was a little bit unhappy with the fact that they didn't have a lot of time. And they also pointed out something that we haven't noticed is that there were some slides that weren't actually matched to the video, which resulted in quite a bit of unhappiness on their part because they're like, oh, but I saw the slide and why wasn't it matched? That's actually started a whole other direction in my research, because it's like, why weren't they matched? And it's a whole new area in which you could actually start matching them. So we noticed that the rotated slides and the animated slides actually cause quite a bit of issues when you're trying to do the matching. So this looks really promising, and I was very happy with the results that we got. So the tool is now actually available online, and in addition to having that online interface, we have the upload interface where you could now easily upload the video and the presentation slides and have it all tagged. So I had the privilege of working with quite a few students, both undergraduate and graduate students, who have helped me put it together using the upload or the main portal interface. And so now what I'll do is I'll just wrap it up and open up the floor to questions for some of the things that I haven't yet covered. Who's brave enough for the first question? Yes?
So what's your, on average, what was your accuracy for matching slides?
Excellent question. So it's, if you have what's known as a slide cast, where you mainly see the slide, then we get a 100% accuracy. If it's not a challenging condition and it's pretty distinct slides, then we can match it with pretty high accuracy. The cases where we have challenges, and I'll pull up a slide, maybe not, where we have problems like when the speaker is walking in front of the slide, sometimes they actually tap the screen, and that makes the key points, even the same key points, not look the same because they're now spread out. Then the accuracy can drop to maybe 70%, 80%. If we have really challenging lighting conditions, so if somebody flips the light on and off, then the camera usually takes a little while to adjust, and sometimes you see that the slide is completely washed out. So we manually tag the slides, and we know that which slide was shown, but when we ask the computer to match it, it's like it's a completely white slide, so there is no slide. And even though it's sort of correct, we mark it as an incorrect result. So, but overall, we were pretty impressed with how well this is working. Yes?
This may be a given, I didn't know it, or if it was even useful. I mean, when you're going through the slides, does your system also take into account the more likelihood that they're likely to go to either the next or previous slide when it's calculating? So if it's less sure about the next slide, it can take into account what it saw before?
Yeah, that's a brilliant question. Did we ever take into account the probability of going back or forward a certain number of slides from the slide that we detected? And yes, there was a student that actually looked into creating this probability distribution, and the probability distribution showed that it is more likely that the presenter will move forward than backward. And yes, given that we had a slide, if maybe we weren't sure about it, we would look at the probability distribution to compute this. The challenge comes in with the fact that you have presenters who have very different presentation styles, and once again, if you have animated slides, that assumption doesn't quite work. But yeah, it's a really interesting direction to see. It also depends on which data set you train it on. So the more data you give it, the better it might get at figuring out that distribution. Yes?
Could you increase the success rate in the matching by having high definition photos and videos rather than lower definition?
Yes. So the higher the definition of the video and the slides, the more accurate the key points will be, the much more likely it will be that you will find the correct match. So absolutely. The downside of having, anyone sees the downside of having high resolution videos and pictures?
More costly in resources?
More costly in resource. So the storage is relatively cheap, so it's not as bad to store those. But you're right that high resolution files do take up a lot more storage space, and they also take more time because you will have a lot more key points for an image that is 3,000 by 4,000 than on an image that is 1,400 by 800. So there is an inherent trade-off. But yes, if we had super powerful machines, unlimited amount of storage space, we could definitely do this a lot more reliably. Yes. Very good questions. Other questions, other thoughts, possible directions. Yes?
The homography matrix is a 3 by 3 matrix, right?
Yes.
What is the interpretation if you have a 4 by 4 matrix?
That's a very good question. So in homography, when you have a 4 by 4 matrix, that's a full camera matrix that has homography embedded in it. So there could be either so if you just tell me I have a 4 by 4 matrix, it can be a camera matrix, it can also be a fundamental matrix. That basically says that, oh, I might have two cameras that are looking in the world from two different directions, and in order to go from one into the world and into the other, I can bypass that and go from one into the other. And so that could be one of the interpretations if I just see a particular matrix. But if it's a camera matrix, then it has the homography sort of embedded in it, and it has an extra set of parameters telling me where is the camera actually located in space. So it has the translation vector that is, given that this is an origin, this is how far it's offset. And we have more parameters for the focal length and the imaging plane. Yes?
Did you consider using like an OCR system
Ooh.
as a feature? And if so, did you test and was it effective?
Yeah, so did I consider using optical character recognition as a possible feature? We did not, because we tested it using the optical character recognition. The problem came from a few talks that we had where the speaker had absolutely no slides, no words on the slide, and just images. It was a biology talk that had formulas and molecules and the DNA, and so the optical character recognition was essentially useless, and it just added the overhead, and it performed just as well when we used this key point features, so we decided to stick with that. But yeah, that's very helpful. One of the directions that I'm eagerly watching is to have the automated speech recognition improve, because we have in the interface the ability to search, and essentially we're searching within the slides, but as soon as the automated transcript becomes very reliable, then I can search for words that the speaker said that may not have appeared on the slide as well. So that would be where the text and the verbal information would be very useful. You had a question? Yeah.
In the Runsack process, once you found the homography and took out the outliers, then what was the metric you used to find the best slide? Was it just the number of true matches?
Yeah, we tried several, and we decided to stick with the top match that top slide that produced the most matches.
Okay.
Yes.
And what did you do to account for that a slide is going to be shown for several seconds? That means about several hundred images for the same slide. Because it's 30 frames per second, so,
Yes.
so your slide is there for possibly more than a couple of seconds, and so you have many images and one slide. Did you take that into account to help the system?
Yeah, so we, for a while, have been subsampling the videos. So we said, well, we have 30 frames for just 1 second. If you have a 30-minute talk, that's a lot of frames. And so, well, maybe we can go and look at every 100th slide. One of the directions that I'm currently working on is, can we intelligently look through the video and just pick out the frames that are key frames, where something interesting happened. Not just randomly and arbitrarily say that I will take every 100th one, but just have some sort of notion, what is the reason why we picked out those frames, and looking at different features that we can use as a way to say, okay, we can break it up here and pick this frame because it's maybe representative of that chunk where just single slide was shown and nothing else was happening in the video.
Right.
Yeah,
Other questions?
really good questions. Yes.
And this might be once again, I'm not sure about this question, but I mean, how active is the development on this? For example, like I know that when I was doing research before this, I went to your site and it didn't look like there was a ton of really recent stuff. Is it a project you do with your students over time, or?
Yeah, so it was a lot more active during the time that I was doing my PhD. A lot of the students have this unfortunate trend of graduating and leaving. It hasn't. We haven't updated the site since I think last year or the year before, and so most of the development that is happening is now on the research side, writing the paper and putting in the results. And I'm trying to see if I can somehow get it started up again. A lot of people, whenever they look at this project, tell me that I should just quit my professor job and start a startup and offer it as a software as a service. So who knows? Maybe one day it will be a lot more active. Yes?
Did you try using the half transform to determine the match?
Half transform. Half transform really relies on the lines.
Yeah.
So it's kind of looking at those. And well, I guess we were thinking about half line transform, and then we got the slides where it was really lots of images, and it wasn't as useful.
Applicable.
Yeah, but I am looking for new features that we can bring in other than SIFT and see if maybe that will be faster or more reliable. So it was, the way we structured it is that we have all of these different components that we can swap out and then test to see, did the matching improve? Did this help? Did the speed increase? Yeah.
Any questions?
Other questions? I love